Hello there, welcome to CXC Math TV. Today's topic is going to be how do we go about solving matrix equation? And this is a part one of two-part videos. Now, we're gonna have to review some properties of matrices, some new properties. The first property is known as determinants. Now, let's say a matrix A is given by A, B, C, D. Now, you're going to see two lines between it, slash A. That means the determinant of the matrix A. Alright, so you see A in between two lines. It is also written sometime as DETA, meaning the determinant of the matrix A. Now, the determinant of a matrix A is computed by AD minus BC. Now, this can be read as the product of the leading diagonal minus the product of the non-leading diagonal. So look at it this way. To find the determinant of A, we multiply, look at that blue arrow there, A times D, minus, look at the next arrow, B times C. So it's product of leading minus product of non-leading. That's how we find the determinant. And so let's look at this example right here. Let's say the matrix A is 2, 1, 3, 5. Find the determinant of A. So the determinant of A is going to be 2 times 5, the blue arrows, we multiply those, minus 1 times 3. That works out to be 10 minus 3, which is 7. So the determinant of the matrix A is 7. Let's look at another one. Let B be 5, 7, negative 2, negative 4. Find the determinant of B. Pause and attempt this question here. So the determinant of B will be 5 times negative 4, which we know is negative 20, minus 7 times negative 2, which we know is negative 14. So minus 20 minus minus 14, that works out to be negative 6. So the determinant of B is negative 6. Nice. Now look at this question here. Given the matrix M is defined by M is equal to R squared 5R 20, and the determinant of M is 25, what is the value of R? Now pause and attempt. Now to do this question, we have to start by saying the determinant of M is R squared times R, right? Because leading diagonals, R squared times R, minus non-leading diagonal, the 5 times the 20. And it's equal to 25. That's because the question told us that the determinant of M is 25. R squared times R is R cubed, minus 5 times 20 is 100, and that's equal to 25. We bring over the 100 to the right hand side. To get R cubed is 125, and so that implies R would be the cube root of 125, which is 5. And so the value of R is 5. Nice. Now, after we learned that about determinants, there is something known as singular and non-singular matrix. Now, a singular matrix is a matrix whose determinant is equal to 0. Remember that. And a non-singular matrix is a matrix whose determinant is not equal to 0. Here's a typical example. Given the matrix M is K negative 3, 4, 1, and M is a singular matrix, find the value of K. Now we know that the determinant of M is going to be K times 1 minus negative 3 times 4. But since they told us it is singular, we equate it to 0. And so we get K minus minus 12 equals 0. And minus become plus, so we get K plus 12 is 0. And so K equal to negative 12. So K is equal to negative 12. That's the value of K that will make this matrix singular. Here's another question for you to try. Given that N is a singular matrix, Y 2, negative 4, 1, find the value of Y. Pause and attempt. Now in doing this, we're just going to say that the determinant of N is Y times 1 minus negative 4 times 2. That's Y minus minus 8, which becomes Y plus 8. And since it is singular, we equate it to 0. And so y plus 8 is 0. And so y equal to negative 8. Now sometime you may get a question like this. State which of the following matrix is singular or non-singular. And they give us the matrix A, B, and C. So pause and attempt. As we pause and attempt, we realize the determinant of A is 3 times 4 minus 1 times 2, which is 10. Since it is not singular, in red color we can write A is non-singular. Let's look at B. Negative 2 times negative 3 minus 5 times 1, that works out to be 1. Now that is still not 0, and so we say that the determinant of B is 1. And so B is non-singular because it's not 0. Let's look at C. 4 times 3, which is 12, minus negative 2 times negative 6. And that works out to be 12 minus 12, which is 0. And so we get 0, and so C is a singular matrix. Beautiful, C is a singular matrix. Nice. The next thing to look at now is adjoints. That is the next property of matrices we're going to look at, which is adjoints. Now, given the matrix A is A, B, C, D, the adjoint of the matrix A is written as D minus B minus C A. Now, you're probably saying, whoa, what is that? Let's slow down. The adjoint of A is found by interchanging the leading diagonals, and the non-leading diagonals, we then multiply those by negative 1. Alright, so whenever we have the matrix A is A, B, C, D, you see that blue arrow, we're going to switch where A is. We're going to put A where D is and D where A is. And then the non-leading, the B and the C, we just multiply it by negative 1. Let's look at some examples. It always gets easier with examples. Find the adjoint of the following matrix. A is 3, 2, 1, 4. B is negative 2, 5, 1, negative 3. And C is 4, negative 6, negative 2, 3. So we write down the matrix A. Alright, and so the adjoint of A is, we interchange the 3 and the 4. Cool. Alright, so the 4 goes where the 3 is. Then we multiply the 2 and the 1 by negative 1. So the adjoint of A is 4, negative 2, negative 1, 3. So pause and work out the adjoint of matrix B. So of course we start by interchanging the negative 2 and the negative 3. And then we multiply the 5 and the 1 by negative 1. So the adjoint of B is negative 3, negative 5, negative 1, negative 2. And pause and attempt and find the adjoint of C. We should be getting 3. Put the 3 where the 4 is and the 4 where the 3 is. And multiply negative 6 times 1 to get 6. And multiply negative 2 times 1 to get 2. So the adjoint of C is 3, 6, 2, 4. Beautiful. Nice. Now there's another property of matrix that we must know before we can solve equations. And this is known as the inverse of a matrix. The inverse of a matrix is denoted by A raised to the minus 1 if the matrix is A. Alright? And the inverse of the matrix is found by, it's equal to 1 over the determinant multiplied by the adjoint of the matrix A. So we just learned how to find determinant and adjoint. So the inverse is 1 over the determinant times the adjoint. So it's 1 over A times D minus B times C times the adjoint. And we know we interchange the A and the D and multiply the B and the C by negative 1. So let's look at some examples. Given the matrix P equals 7, 8, 5, 6, find P inverse. To do this question, step 1, we find the determinant of P. So that's 7 times 6 minus 5 times 8, 42 minus 40, which is 2. Good. Step 2, find the adjoint of the matrix. We interchange the 6 and the 7. So put the 6 where the 7 is and the 7 where the 6 is. I will multiply the 8 and the 5 by negative 1. So we'll get the adjoint of P is 6, negative 8, negative 5, 7. Step 3. Use the inverse matrix formula. So in this case, we're going to write P inverse is equal to 1 over the determinant of P times the adjoint of P. So it's 1 over the determinant of P is 2, so it's 1 over 2. times the adjoint of P, 6, negative 8, negative 5, 7. So half times 6 is 3, half times negative 8 is negative 4, half times negative 5 is negative 5 over 2, half times 7 is 7 over 2. So the inverse of the matrix P, which is P inverse, is 3, negative 4, negative 5 over 2, 7 over 2. That gives you the inverse of the matrix P. Really nice. So here are a couple more questions for us to do. We're going to pause and attempt. So find the inverse of the following matrix, A and B. So start with part A, do part A. As you should have paused and attempted, we're going to start by finding the determinant. So that's negative 2 times negative 3 minus 1 times 5. 6 minus 5 is 1. Next thing we do is find the adjoint of A. We interchange the negative 2 and the negative 3. Or multiply the 1 and the 5 times negative 1. So that's negative 3, negative 1, negative 5, negative 2. Then we use the inverse formula. 1 over the determinant, which is 1, times the adjoint, negative 3, negative 1, negative 5, negative 2. Now 1 times anything is just itself, and so the inverse of the matrix A is negative 3, negative 1, negative 5, negative 2. Cool. Now let's look at matrix B. Pause and attempt on the matrix B. In doing matrix B, we should realize B is 3, 6, 1, 2. So first we find the determinant. 3 times 2, which is 6, minus 1 times 6, which is 6. 6 minus 6 is 0. Then we find the adjoint. The adjoint is 2, negative 6, negative 1, 3. Then let's use the inverse formula. So it's 1 over the determinant of B times the adjoint. But look at that. The determinant is 0. Oh my God, the determinant is 0. What is 1 over 0? We do not know. Because our calculator cannot evaluate 1 over 0, then in this case, the inverse of the matrix B does not exist. Now, what did you observe? The inverse of matrix B does not exist, but look at this. So it's important to note that whenever the determinant of a matrix is 0, we call that a singular matrix, and the inverse does not exist for a singular matrix. So we must remember that. Alright, that the inverse does not exist for a singular matrix. Alright? Now, let's look at some more properties of matrices here. Now look at this. The matrix M is 3, 1, 4, 2. Find the matrix M times M inverse. If you find the inverse of M, it's 1 over the determinant, 3 times 2 minus 1 times 4. And then we multiply it times the adjoint. 2, negative 1, negative 4, 3. And we get a half of 2, negative 1, negative 4, 3. Which works out to be 1, negative a half, negative 2, 3 over 2. That's going to be the inverse of M. But the question said find the matrix M times M inverse. Now M times M inverse is going to be 3, 1, 4, 2 times 1, negative a half, negative 2, 3 over 2. So we go row by column, 3 times 1 plus 1 times negative 2. Then row by column again, 3 times negative a half plus 1 times 3 over 2. Then we'll go second row times first column, 4. So multiplying M times M inverse, we end up get 3 minus 2, which is 1. Negative 3 over 2 plus 3 over 2, that's 0. 4 minus 4, that's 0. Negative 2 plus 3, that's 1. So notice that M times M inverse gives us 1, 0, 0, 1. Now, important to note, this matrix 1, 0, 0, 1 is known as the identity matrix. So we say I is equal to 1, 0, 0, 1. Whenever we multiply a matrix times its inverse, we obtain the identity matrix. So anytime you multiply a matrix A times its inverse, you're going to get the identity matrix. Another example to verify it, if you write down the matrix A, which is negative 2, 1, 5, negative 3, you can multiply it by its inverse. And we know the inverse of that is negative 3, negative 1, negative 5, negative 2 from previous questions above, right? It's the same matrix A where we found the inverse already. When you multiply A times A inverse, showing all of the steps right here, you're going to simplify down to give us that A times A inverse works out to be 1, 0, 0, 1, which is I, because we call that matrix I. So anytime you multiply a matrix times its inverse, you're always going to get the identity matrix. Now, what is so special about this identity matrix? Now, whenever we multiply a matrix times its inverse, we obtain the identity. And also, any matrix multiplied by the identity matrix give back the original matrix. For example, the same A, negative 2, 1, 5, negative 3. We're going to prove that when we multiply A times the identity matrix, we're going to get back A. So negative 2, 1, 5, negative 3 times 1, 0, 0, 1. We go row by column. Negative 2 times 1 plus 1 times 0. And then we'll go negative 2 times 0 plus 1 times 1. 5 times 1 plus negative 3 times 0. And then 5 times 0 plus negative 3 times 1. That works out to be negative 2, 1, 5, negative 3. But that is still A. So realize that when we multiply any matrix A times the identity, we get back our matrix A. Alright? So the takeaway from the videos is, given the matrix A, the determinant is found by leading diagonals, the product A times D minus B times C. The adjoint of the matrix A is you interchange the leading diagonals and then multiply the non-leading diagonals by -1. And then the inverse of a matrix, A inverse, is found by 1 over the determinant multiplied by the adjoint. That's what we should take away from this video. Alright, so that's it for today. Stay tuned for more as we'll continue looking at how to solve matrix equations. Alright, so stay tuned for the next video. And until next time, see you soon and have a blessed day.